Hello students, welcome to our YouTube channel Experience Tutor. Today we'll discuss class 12th physics get more than 95% marks series Electromagnetic Induction chapter 6 ncert line by line part 1. Before we begin our today's class, we have a humble request for you. Please subscribe our channel if you have not subscribed yet. Please like and share our videos among your friends and relatives so that they too get benefited, and please click on the bell icon so that you can get automatic notification whenever a new video is uploaded by us. In this way you will not miss any of our important videos. Let us begin today's class. 6.1 Introduction. Electricity and magnetism was considered separate and unrelated phenomena for a long time. In the early decades of 19th century, experiments on electric current by Ørsted, Ampere, and few others established the fact that electricity and magnetism are interrelated. They found that moving electric charge produce magnetic field. For example, an electric current deflects a magnetic compass needle placed in its vicinity. This naturally raised the questions like, is the converse effect possible? Can moving magnet produce electric current? Does the nature permit such a relation between electricity and magnetism? The answer is re resounding yes. The experiments of Michael Faraday in England and Joseph Henry in USA, conducted around 1830, demonstrated conclusively that electric currents were induced in closed coil when subjected to change the magnetic fields. In this chapter, we will study the phenomena associated with the changing magnetic fields and understand the underlying principle. The phenomena in which electric current is generated by varying magnetic field is appropriately called electromagnetic induction. So in this paragraph, basically it is saying that before it was believed that electric electricity and magnetism are two separate things, but after few experiments made by the scientists like Ampere, Ørsted, and few other great scientists, and proved that electricity and magnetism are interrelated. So in in the first decade of 19th century, it was found that another two scientists, Michael Faraday in England and Joseph Henry in USA, conducted few experiments where they have proved that if the magnetic field is changed, then current is induced in a closed coil. And this induced current was known as this current was known as induced current, and this phenomena was known as electromagnetic induction. Let us see the next paragraph. When Faraday first made public his discovery that relative motion between the bar magnet and a wire loop produce a small current in the latter, means in the coil. He was asked, "What is the use of it?" His reply was, "What is the use of a newborn baby?" The phenomena of electromagnetic induction is not merely of theoretical or academic interest but also of practical utility. Imagine a world where there is no electricity, no electric light, no trains, no telephones, no personal computers. The pioneering experiment of Faraday and Henry have led directly to the development of modern day's generator and transformers. Today's civilization owes its progress to the great extent to the discovery of electromagnetic induction. So, in this paragraph, basically, the main important things that generator and transformer are the two great inventions based on electromagnetic induction. Topic 6.2, the experiments of Faraday and Henry. The discovery and understanding of electromagnetic induction are based on a long series of experiments carried out by Faraday and Henry. We shall now describe some of these experiments. Experiment 6.1. Figure 6.1 shows a coil C1 connected to a galvanometer G. So let us see the figure. So this is the coil C which is connected to a galvanometer. This is the coil C and which is connected to a galvanometer G. When the north pole of the bar magnet is pushed towards the coil. So this is the north pole of the bar magnet and it is pushed towards the coil. The pointer in the galvanometer deflects. So this pointer in the galvanometer deflects. Now indicating the presence of electric current in the coil. The deflection lasts as long as the magnet is in motion. The galvanometer does not show any deflection when the magnet is held stationary. When the magnet is pulled away from the coil, the galvanometer shows deflection in the opposite direction, which indicates the reversal of the current's direction. Moreover, when the south pole of the bar magnet is moved towards or away from the coil, the deflection of the galvanometer are opposite to that observed with the north pole for similar movements. Further, the deflection and hence current is found to be large when the magnet is pushed towards and pulled away from the coil is faster. Instead, when the bar magnet is held fixed, the coil C1 is moved towards or away from the magnet, the same effect is observed. It shows that it is the relative motion between the magnet and the coil that is responsible for generation induction of electric current in the coil. So this experiment is quite simple one. So we have a coil, we have a galvanometer attached with the coil. Now we take a bar magnet. First we uh, push the north pole of the magnet towards the coil. So as soon as it is moving, the galvanometer indicator shows deflection. Pointer shows deflection. As, as soon as the magnet is stopped moving, the galvanometer pointer also stops. Similarly, if we move the south pole towards the coil, uh, the same effect was observed, but the direction of the galvanometer pointer was opposite to that of north pole for the same action. Now, if we keep the magnet stationary and move the coil, rather move the coil towards the magnet, the same effect was observed. If we have moved the magnet little faster, then the pointer shows more deflections. And in this way, it was proved that while moving a magnetic field or field it, within a closed coil, a current is generated. Experiment 6.2. In figure 6.2, the bar magnet is replaced by a second coil C2 connected to a battery. The steady current is in the coil C2 produce a steady magnetic field as coil, coil C2 is moved towards the coil C1, the galvanometer shows a deflection. So we can see this arrangement in this figure 6.2. This indicates that electric current is induced in coil C1. When C2 is moved away, galvanometer shows a deflection again, but this time in the opposite direction. The deflection lasts as long as C2 is in motion. When the coil C2 is held fixed and C1 is moved, the same effect was observed. Again, it is the relative motion between the coil that induced the electric current. Experiment 6.3. The above two experiments involve relative motion between the magnet and a coil and between two coils. The above two experiments involved relative motions between the magnet and a coil and between two coils, respectively. Through another experiment, Faraday showed that this relative motion is not an absolute requirement. Figure 6.3 shows two coils C1 and C2 held stationary. Coil C1 is connected to a galvanometer with while the second coil C2 is connected to a battery through a tapping key. It is observed that galvanometer shows a momentary deflection when tapping key K is pressed. The pointer in the galvanometer returns to 0 immediately. If the key is held pressed continuously, there is no deflection in the galvanometer. Then the key is released, a momentary deflection is observed again, but in the opposite direction. It is also observed that deflection increases dramatically when an iron rod is inserted into the coil along their axis. So this was also a simple experiment which is self understood, so nothing to explain here. Section 6.3 Magnetic Flux. Faraday's great insight lay in di- discovering simple mathematical relation to explain the series of experiments he carried out on electromagnetic induction. However, before we state and appreciate his law, we must get familiar with the notation of magnetic flux phi b. Magnetic flux is defined in the same way as electric flux is defined in chapter 1. Magnetic flux through a plane area A placed in a uniform magnetic field B, figure 6.4, can be written as phi b is equal to B dot A. So dot product of B and A, that its magnitude is BA cos theta, where theta is the angle between B and A. The notion of area as a vector has been discussed earlier in chapter 1. Equation 6.1 can be extended to curved surface and non-uniform fields. If the magnetic field has different magnitude and direction at various part of the of a surface as shown in figure 6.5, then the magnetic flux through the surface is given by phi b is equal to phi n is equal to b dot da1 b1 dot da1 plus b2 dot da2 plus dot and sigma all bi dot dai. This is equation 6.2. So 6.1 is simple, just it is given phi b is equal to b dot a, where a is the area and b is the magnetic field, uniform magnetic field, and its magnitude is b a cos theta, where a theta is the angle between b and a. Fine. So if we consider that there are various fields and acting on various areas, then we have a different magnetic flux, and it is equal to the summation of different magnetic flux acting on the different area. For example, phi n is equal to b1 dot da1. Da1 is the area and b1 is the magnetic field acting on that area. So magnetic flux of that area is b1 da1. Again, area is say d2 da2, and magnetic field on that area acting on that area is b2, then that part, magnetic flux of that part is called b2 dot da2. In that way it goes on. Now, where all stands for summation of overall area of element dai, comprising the area, and bi is the magnetic field of the area element dai. The SI unit of magnetic flux is Weber WP, or Tesla meter squared, Tm square. Magnetic flux is a scalar quantity. Now 6.4, Faraday's law of induction. From the experimental observation, Faraday arrived at a conclusion that an EMF is induced in a coil when, so what was the conclusion? An EMF is induced in a coil when magnetic flux through the coil changes with time. Experimental observation discussed in section 6.2 can be explained using the concept. the motion of the magnet towards or away from coil C1 in experiment 6.1 and moving a current carrying coil C2 towards or away from coil C1 in experiment 2 changes the magnetic flux associated with the coil C1. The change in magnetic flux induced the EMF. So basically this change in magnetic flux induced EMF in the coil C1. It was this induced EMF which caused electric current to flow in the coil C1 and through galvanometer. A possible explanation for the observation of experiment 6.3 is as follows. When tapping key K is pressed, the current in the coil C2 and the resulting magnetic field raise from 0 to maximum value in short time. Consequently, the magnetic flux through the neighboring coil C1 also increases. It is the change in magnetic flux through coil C1 that produces the induced EMF in coil C1. When the key is held pressed, current in coil C2 is constant. Therefore, there is no change in magnetic flux through the coil C1 and the current in coil C1 dropped to 0. When the key is released, the current in C2 and resulting magnetic field decreases from maximum to 0 in short time. This results in a decrease in magnetic flux through coil C1 and hence again induced electric current in coil C1. The common point in all these observations is that the time rate of change of magnetic flux through a circuit induced EMF in it. So, what is the common take? That the time rate of change of magnetic flux through a circuit induced EMF in it. Faraday stated experimental observation in the form of law called Faraday's law of electromagnetic induction. The law stated below. The magnitude of induced EMF in a circuit is equal to the time rate of change of magnetic flux through the circuit. So this is the law. The magnitude of induced EMF in a circuit is equal to the time rate of change of magnetic flux through the circuit. Mathematically, we can write the induced EMF is given by E is equal to minus d phi by dt. The negative sign indicates the direction of E and hence the direction of the current in a closed loop. This will be discussed in detail in the next section. In the case of closely wound coil of n turns, change of flux associated with each turn is same. Therefore, the expression for the total induced EMF is given by E is equal to minus n d phi by dt. This is equation 6.4. The induced EMF can be increased by increasing the number of turns n of a closed coil. So it is important that the induced EMF can be increased by increasing the number of turns n of the closed coil. From equation 6.1 and 6.2, we see that the flux can be varied by changing any one or more of the term b, b, a, and theta. In experiment 6.1, 6.2, and section 6.2, the flux is changed by varying b. The magnetic the flux can also be altered by changing the shape of the coil, that is, by shrinking it or stretching it in the magnetic field, or rotating the coil in the magnetic field such that the angle theta between B and A changes. In these cases too, an EMF is induced in the respective coils. So these are self-explanatory, very properly explained. Now let us see example 6.1. Consider experiment 6.2. What would be what would you do to obtain large deflection of galvanometer? B. What would you demonstrate the presence how would you demonstrate the presence of an induced current in absence of galvanometer? Solution. First one, A. To obtain the large deflection, one or more of the following steps can be taken. First, use the rod made of soft iron inside. Use a, use a rod made of soft iron inside the coil C2. Second, connect the coil to a powerful battery. Third, move the arrangement rapidly towards the test coil C1. B. Replace the galvanometer by a small bulb, the, the kind one find in a small torch light. The relative motion between the two coils will cause the bulb to glow and thus demonstrate the presence of induced current. In experimental physics, one must learn to innovate. Michael Faraday, who is ranked as one of the best experimentalist ever, was legendary for this innovative skills. Now example 6.2. A square loop of side 10 centimeter and resistance 0.5 ohm is placed vertically in the east-west plane. A uniform magnetic field of zero point 0.1 Tesla is set up across the plane in the northeast direction, and the magnetic field is decreased to zero in zero point 0.7 seconds at a steady rate. Determine the magnitude of induced EMF and current during the time interval. So, first thing, whatever is given in the question will mark it. The angle theta is made by the area vector of the coil with the magnetic field is 45 degree. From equation 6.1, the initial magnetic flux is phi is equal to ba cos theta. So put the values, we get we get the value of phi. Final phi is minimum final. Flux phi minimum is equal to 0. The change in flux is brought about in zero point 0.7 seconds. From equation 6.3, the magnitude of the induced EMF is given by E is equal to modulus of delta phi B upon delta T. So, which is equal to modulus of phi minus 0 upon delta T. Why 0? Because initially the magnetic flux value was 0. So put the value of phi and delta T, we get 1 MV. And the magnitude of the current is I is equal to E by R. Therefore, E's value is 10 to the power minus 3 volt upon R's value is 0.5 ohm, and we get 2 milliampere of current. Note that the Earth's magnetic field will also produce a flux through the loop, but it is a steady field which does not change within the time span of the experiment and hence does not induce any EMF. Now, experiment example 6.3. A circular coil of radius 10 centimeter. So, a circular coil of radius 10 centimeter, 500 turns and resistance to ohm is placed with its plane perpendicular to the horizontal component of the Earth's magnetic field. It is rotated about the vertical diameter through 180 degree in 0.25 seconds. Estimate the magnitude of the EMF and current induced in the coil. Horizontal component of the Earth's magnetic field at the place is 3 multiplied by 10 to the power minus 5 Tesla. Solution. Initial flux through the coil phi b initial is equal to b a cos theta. Put the values, we get 3 pi into 10 to the power minus 7 Weber. Final flux after the rotation phi b final is equal to, put the values, you will get minus 3 pi 10 to the power minus 7 Weber. Therefore, estimated value of induced EMF is E n d phi by dt. Put the values and we get 3.8 into 10 to the power minus 3 volt, and I is equal to E by R, and put the values, we get 1.9 into 10 to the power minus 3 ampere. Note that the magnitude of E and I are the estimated values. Their instantaneous value are different and depend upon the speed of the rotation of the particular instant. So let us skip till here for today. Next class will start with 6.5 Lenz's law and conservation of energy. So let us review what we have done today. Today we have started with the introduction. In the introduction, it is told that initially it was believed that magnetic and electricity and magnetism are treated separately on initial days. Then Faraday and Western uh, and other scientists proved that they are interrelated, and they have Faraday has have done few experiments, and on the basis of those experiments, he had a concept. He had derived the concept uh, in, of electromagnetic induction, and due to that, generators, transformers uh, were possible to build. In the section 2, we have studied about few experiments where magnet is moved towards the coil, or a current passing coil is moved towards another closed loop coil. Then we see that current is induced, EMF is induced in the closed loop coil, and so the current flows, induced current flows in the closed loop coil. So there were three experiments done by Faraday, and on the basis of these experiments, it he has came up with the Faraday's law of electromagnetic induction. So, and again, we have also done about the concept of magnetic flux, So, and we came to know about magnetic flux is equal to B dot A, where B is the magnetic field and A is the area element, and so B dot and theta is the angle between B and A. So B dot A is equal to B A cos theta. If if we consider a object where a different area element is experiencing different magnetic fields. For example, area element dA1 is experiencing a magnetic field B1. Similarly, area element dA2 is experiencing the magnetic field B2, and in this way so on. Then the total magnetic flux for n area element phi n is equal to B1 dA1 plus B2 dA2. In this way it will go on, and finally we get sigma all Bi dot dai. So sigma all, so all stands for all the elements, all the area elements. The unit SI unit of magnetic flux is Weber or Tesla meter squared, T meter square. So, and magnetic flux is a scalar quantity. So Faraday's law of magnetic induction, where the law mainly states that the time rate of change of magnetic flux through a circuit induced EMF in it. Thus, induced current is flown through the circuit. So this is the basic law of Faraday's law of electromagnetic induction, that the time rate of change of magnetic flux through a circuit induced EMF in it, and this is known as Faraday's law of electromagnetic induction. And mathematically we have written that uh, E is equal to minus d phi b by dt. The negative sign indicates the direction of E and hence the direction of the current in the closed loop. If the coil has n turn, then we can also write E is equal to minus n d phi b by dt. The induced EMF can increase by increasing the number of turns of a closed coil. And we have done few of the numerical examples. In the next class, we'll go through the concept 6.5 Lenz's law and conservation of energy. Before we end our today's session, we request you to subscribe our channel if you have not subscribed yet. Please like and share our videos among your friends and relatives so that they can also get benefited of it. And please click on the bell icon so that you can get automatic notification whenever any video is uploaded by us, and you will not miss any single video. Thank you for supporting us and watching our videos. Thank you very much.